In this example, we'll be looking at an open channel flow application. Recall that open channel flow is when we have water where the water surface is open to the atmosphere. So in this example, we have a cross section. It's trapezoidal, but kind of a hybrid trapezoidal. It's got a total depth of 7.2. Okay, the base of the channel is 12 feet wide. This slope has a 2 to 1, 2 horizontal to 1 vertical. This slope here is a 1 to 1. And we know that both this height and this height here are 5 feet. Okay, we're given the flow of the channel as 6350 CFS. We know the roughness, which is a Manning's N, 0.011, and we also have the slope of the channel as 0.012. Okay. I'm going to take you through 3 different calculations. The first one will be to determine the hydraulic depth. There will also determine what the velocity of the flow is. And then lastly, we'll classify the flow by calculating the Frew number. So let's go ahead and look at the hydraulic depth. Okay. The hydraulic depth is equal to the area over the top width. Okay. So let's go ahead and do these calculations. I'm going to start with the top width. Now, if I know that this depth here is 5 and the slope is at a 2 to 1, then this piece right here is going to be 5 feet from this corner to the edge. Likewise, if this depth is 5 feet and it's a 1 to 1 slope, then this dimension here is actually 5 feet. Oh, looking at my numbers, I see that's not 5 feet. That would be 10 feet. There we go. So, the total width of this flow, right, is going to be the 10 feet plus the 12 feet plus the 5 feet. Okay? And let me go and carry that over. That's 27 feet. Okay? Now the area, the way I'm going to do it, there's lots of different ways, but I'm going to take the entire rectangle here, okay, which has a width of 27 and a height of 7.2. Okay, and I'm going to subtract out these 2 triangles. Okay, now the area of this triangle, I have a triangle that would be 5 high by 10 wide. Okay, so that area is 1/2 5 times 10, or 25. Okay, this one here is a triangle that's 5 by 5, which is 25, and again, we're taking half of that, which would be 12.5. Okay, so if I take 7.2 times 27, I subtract 25 and subtract 12.5, okay, I get an area of 156.9 feet squared. Okay, so based on that, I get a hydraulic depth of 5.81 feet. Okay, so I'll go ahead and box that here. The hydraulic depth, 5.81 feet. Okay, so that's part A. Let's do part B now. Now in part B, a lot of you guys are going to think, all right, we know the flow, we calculated the area, couldn't we just use continuity equation? Couldn't we just say Q equal VA and solve for V? But in this particular case, there's a lot more to it than that. First of all, we know the slope of the channel. So this is slope meaning from, going upstream, going downstream. The slope of the channel itself is given. And we also know the roughness of the channel, which is basically friction factor. So having these 2 parameters here tell us that, in an open channel flow application, if we know Manning's N and we know the slope, we definitely should be using the Manning's equation to calculate the velocity. The general form of the Manning's equation is V is equal to, it'll be 1.49, right, for the English version, N, and then we have the hydraulic radius to 2/3, and then we have our slope. Okay. So when I look at this equation, I'll be solving for the velocity. I know N, now it's given to me, and I know the slope. The one thing I don't know is this hydraulic radius. So I'm going to have to do the hydraulic radius calculation to get that velocity. Okay. The hydraulic radius is the area over the wetted perimeter. Now we calculated for the area already up here. So we're going to need this wetted perimeter, okay? I'll just write the wetted perimeter right next to it here. What the wetted perimeter is, it's not the perimeter of the entire cross section, it's the perimeter where the water is in contact with the channel surface, like if it's the earth surface, or it could be if it's a pipe and it's partially full. It's where the water's just in contact with the pipe. It does not include the part that's open to the atmosphere. Okay. Now, if this entire depth is 7.2 and this dimension here is 5, that means this piece right here is 2.2. So what I'm going to do is I'm going to just start, I'll go ahead and start on the left, and I'm going to just start adding up all the pieces of this perimeter, figure out what that final wetted perimeter value is. So I start here with 2.2 feet. Okay. Then I have to deal with this hypotenuse. Now, using Pythagorean theorem, I know this depth here is 5. I know this dimension here is 10, right? So this piece here would just be the square root of 5 squared plus 10 squared is square root of 125. Then I'm going to add the 12. Then I'm going to add, again, I'm going to do the same thing with the Pythagorean theorem. So I've got, in this case, I have this dimension 5 squared plus this dimension 5 squared. And then the last piece I have is the 2.2. Okay. When I add this up, I get that the wetted perimeter comes out to be 34.65 feet. So I'll go ahead and underline that. Okay. So I have everything I need now to calculate the hydraulic radius. I've got the area, which was calculated earlier, of 156.9 feet squared. And I know the wetted perimeter is 34.65 feet. So this gives me a hydraulic radius. The value comes out to be, is it 4.528. I'll carry it out a little further than I normally do, but just 3 decimal places, all right? Now I can finally solve for the velocity. So I've got 1.49. I know Manning's n is 0.011. I've got the hydraulic radius here that we just calculated at 4.528. Okay, and I'm going to take 2/3 take that to the 2/3, and then I have the slope here as 0.012, and we'll take that to the half. Okay. When I do that, I get a final velocity equal to 40.6, and that would be feet per second. So again, it's a little different. I mean, you can go back and you can do that. If you want to see how it varies with Q equal VA, if you took Q of 6350 and divided by the area here, you can take a look and see how different it is. But again, because we know the roughness of that channel and we know the slope, we definitely should be using the Manning's equation. Okay. The last piece is to classify the flow. We do that by calculating this Froude number, which is the velocity divided by the square root of g times the hydraulic depth. Okay, we have all the terms we need to do this. We have the velocity right here of 40.6 feet per second. Okay. For g, we know that g in English units is 32.2 feet per second squared. And then we know the hydraulic depth that we calculated in part A is 5.81. And notice how all these units cancel out, right? We'd have feet squared per second squared. Square root is feet per second in the denominator. We have feet per second in the numerator. So the Froude number comes out, as it should, a dimensionless term, and it comes out to be 2.97. Okay? Now, if you recall from the lesson, any Froude number over 1 is classified as a supercritical flow. So this will be a supercritical, if I can write it out here, flow. All right. I'll cloud it so we can highlight what that is. So again, taking you through the procedure, using the dimensions of the channel cross-section, we were able to determine the hydraulic depth. Okay. We also were able to determine the hydraulic radius, which led us to the velocity, right here of 40.6 instead of using Q equal VA. and then we went through and classified the flow based on the Froude number using the velocity and the hydraulic depth terms. It came out to a Froude of almost 3, which is clearly a supercritical flow. And that concludes this example.